My job at Inmarsat is to keep the satellites where they're supposed to be. Fortunately, we have some help. Once we've launched the satellite into a geosynchronous orbit, gravity holds it, more or less, in position, which is 36,000 kilometers from the Earth, 1/10 of the distance to the Moon. To do its job properly, the satellite's transmitters and receivers need to be pointed very precisely at the Earth. From space, the Earth appears about the size of this globe. The Earth is hotter than the space around it, so an infrared sensor on the satellite accurately pinpoints the Earth. Spinning disks inside the spacecraft act in the same way as this toy. Onboard computer systems make small adjustments to the axis of this disk, and that's enough to keep the equipment lined up. But there's a problem. The Sun. It's enormous, and its immense gravitational pull accounts for about 90% of the forces trying to move the satellite's orbit. The Moon and variations in the Earth's density make up the rest. The Sun's gravitational pull is not enough to move the satellite out of its orbit around the Earth, but it is enough to affect the orientation of the orbit, which has to be in the same plane as the equator. And this is where we come in. By calculating and then sending very precise instructions to tiny onboard thrusters, we can continually reposition the satellite in a way that counteracts the forces acting on it. And that's the basics of flight dynamics. My name is Nick Matthews, and I'm a senior flight dynamicist.